Okay, E3 concrete. This is obviously lecture about concrete, introduction, properties, composition, acquisition, application, and design considerations for the theme concrete material, concrete, which we talk about. Rocks are a natural material. Concrete is actually a kind of artificial rock. It's compacted by cement and aggregates, sand and aggregates to create an artificial rock-like material. And the interesting thing is by being able to create this artificial material, we're actually able to create the shapes we want. And that makes concrete such an interesting material in its yeah, in our construction environment. Concrete is composed out of cements and aggregates. Aggregates is sand and gravel mixed together with concrete. The more water we add, the more liquid it gets, but the less strength we actually end up having. And it's said that the early concrete technology starts in the Roman Empire. Pantheon is made with, say, unreinforced concrete. So first, cement and aggregate mixtures are used in this structure. And 2,000 years. That's a long time. It's lasting, which brings us to the properties, durability, density, compressive and tensile strength. Interesting wise, very good in compressive strength, could be a lot, very weak in tensile strength. So the cement does deliver some tensile strength, but the material itself is having less tensile strength. Fire resistance is very high, no burnable material being part of concrete, which brings it to be a material which is interesting to deal with. The numbers, characteristic compressive strengths, depending on the aggregates being added, depending on additional components being added to this tensile strength, very limited. Thermal conductivity, well, very high. We do expect the material to be very good in transporting energy. Steel is a lot better, but say the material itself is not a so-called insulating material. And then thermal expansion, Youngulus module, and design life. Design life 100 years. We already saw Pantheon 2,000 years. So design life could be seen very long. The material basically consists out of cement powder, ordinary Portsand cement, for example, aggregates, which is gravel, sand, and water. Additional chemistries could be added to create different performances of the material. When we add more water to, general speaking, I'm not a concrete specialist, and this is not a concrete lecture. This is a lecture about, say, concrete in facades. When we add more water to the concrete, we get it more liquid, which allows us to get more sharp in surfaces. If we add less water, it by the material itself creates a stronger material, and that's exactly this, say, fine definition which we need to deal with. Aggregates, as I said here, about 40%, fine aggregates 25%. So mainly aggregates, mainly sand and gravel to be added, and then there's some water, cement, 10% plus minus as a composition. The acquisition, the material itself is limestone and clay being harvested, being brought into a cruncher and a mixer. Then the mixing happens in a rotating heater device, which brings it to a clinker-like material. Then it's grinded, crunched, and then packed as a material, and then they are being transported to the site where necessary. When we create the concrete itself, we use the cement as just which is manufactured as just defined. Then we need to add water, sand, and aggregates. So cement, sand, and aggregates. Aggregates could have a certain dimension, but they could also be quite large. So if we have a super large concrete structure, not in facades and other disciplines, we may even use huge rocks as aggregates for the material itself. And then this concrete is a liquid material. It needs to be brought in position. It needs to be shaped, and that shaping is happening by molds. So here we see a prefab mold for a facade for a prefab facade. And you see it's a horizontal kind of basin, and the concrete is poured into this basin and then hardens in this basin. And after it is hardened, the basin is taken apart, the mold is taken apart, and then the concrete object happens. That's done in a prefab setup. This is a prefab situation. So it's this mold, the basin where the concrete is filled in. And then if the component, the facade is finished, it's transported to the site, or it's done on site, which is in situ concrete. And here we see the molding system. So it's actually, again, a basin, systematic structured mold, which then has some reinforcement. We'll talk about that later. And then the concrete is poured into it. When hard, the mold is taken apart, and then the concrete wall stays in position as a setup. With a proper mix, as design consideration, with a proper mix, we can define the functionality, the strength, the thermal conductivity, if you go for light concrete, for the material itself. But concrete does not perform very well for tensile stress. It needs a reinforcement. That's the steel reinforcement in concrete, which we use to combine this compressive and the tensile strength of the two materials to get a proper material, which, as we all know, is used in concrete in a very typical way, to have the stress forces being taken by the steel reinforcement and the compressive forces being taken by the concrete as a system. And then, depending to the general layout of the structure, the general layout of the component, and the forces to the component, these systems are added into it. We can do that with steel reinforcement. Steel reinforcement needs to be covered. We come to that in a minute. That could be done in a mesh system. It could be done with short fibers, which is the top picture, which allows us to have, a finer geometry. It could be also done with glass fiber reinforcements. They don't have the difficulties of corroding, so they say exposure to the outside could be less. It could be even stainless steel reinforcement if you want to. This reinforcement, if it is steel, needs to be covered with an outer layer of concrete to not allow any water, humidity getting to the concrete and then starting to corrode it. If this happens, then the steel corrodes, and by then disappearing, the reinforcement system doesn't work in our concrete structure. We have to think about precast, prefab versus in situ. As said, it's a nice material. If we cast it in the shape we want it, we can create the geometry we want, but then we have to make the mold as we want it. So it's either a precast system or an in situ system. In situ means we need to make the mold at the site and then have to take it off. By precast, we can actually make it in a factory and then have to transport the component. So say a quite individual definition or decision for the different setups. Concrete could be used in different applications. The say standard concrete setup, or we go for an which is quite solid structure, which can take a lot of compressive forces, but also is not very good in thermal insulation, so conductivity is high. To go as an alternative into a lightweight structure, which actually means that we have to pump in a certain technology air into the system, and by that creating a lighter concrete structure, which is then performing better qua insulation, but obviously also can't take that much loads. Or we go for an ultra high performance concrete, which means there's more cement in the material itself, and by that it's more it's better able to take compressive forces in the system, as a general outline. It could be used as an principal building material for foundations, main structures, beam, floor, slab, wall systems as say concrete structure. But we also can see this as a prefab components for facade-like structures. These are prefab main structure components of single house or single family houses. We see how they're say transported, assembled, and then brought into position that the outer cladding of a brick system could be added. And then we see this picture here where even the windows are already brought in position. It could be done, it could be used as a masonry brickwork, could be exposed to the outside, could be in the main structure at the inside. as a brick system. It could be used, and that's where this facade thing comes for, as a prefab facade system, load bearing or non-load bearing, depending on the layout. And as we see here, we see the top picture, which is the facade mode already shown, and we see then the bottom picture where all the reinforcement, even the piping for electricity, is brought into this prefab component, and then the concrete is poured on top of it, and then having an additional layer of insulation. This whole prefab unit is stored in the first step. So we see the concrete being poured, and then the cladding is added to it, and the insulation is added to it, and then fine cladding is added to it, and then this whole thing goes to the truck and then to the construction site, where it's used as, in this case, a load-bearing outer layer of an high-rise building facade setup. It could be also a cladding. So if we don't use it as a main structure, it could be also concrete cladding, which is then brought at the outside into on top of a ventilated facade system. You see the picture on the left, which is the typical railing system where we either add other materials like brick or metal, sheet metal, or concrete plates in a certain dimension to be the outer surface of a ventilated facade. We also can have different ways of creating surfaces. There's one way of tensile fabric formworks, fabric molding formworks, which is this picture, or the top left picture. We can add different aggregates, the wood aggregate, or we can create certain images at the surface if we treat the molding, the prefab molding in a certain way to create these additional surfaces. And by that, I close this small lecture about concrete.